Good day to all of you. Myself, Dr. Arvind Sharma, Associate Professor in Physics, Government Denver College, BKN. Today we are going to continue the topic atmospheric effect on propagation of microwaves. How microwave propagation affected by the atmospheric conditions. So we continue this topic. In last lecture, we understand about the general consideration of the attenuation factors and water vapor attenuation we already understand. Today we start from the attenuation due to fog. Attenuation due to fog. Fog can be formed variety of ways. There are many ways fog can be formed depending mostly on the condensation mechanism. We all know that condensation mechanism is the main reason for the fog formation. Generally, we encounter the type of fog which is formed by the cooling of land after sunset by thermal radiation in calm and clear sky. The cool ground produces condensation in the nearby area by condensation of heat. This type of fog mostly prevails at night and does not last long after sunrise. It generally occurs in autumn and winter. Fog attenuation is comparatively smaller at millimeter wavelengths. Fog attenuation is comparatively smaller, millimeter wavelength. Fog is composed of spherical water droplets, suspended spherical water droplets, which with radii small enough to keep them suspended in air. Their radii are small, so they are suspended in air by microturbulence. And in this bracket, this is the reference, author Liebe et al., Liebe and others in 1989. Attenuation due to fog in the millimeter wave band is mainly caused by absorption and scattering, which in turn depends on the extent of the fog density. In other words, visibility. Fog density or visibility, and its index of refraction. According to Gibbons, the fog density is given in terms of visibility, V in kilometer by M equal to fog density M equal to 0.024 upon V whole power 1.54 per gram cube. Figure 2 shows, what is the figure 2? This is the figure 2. Figure 2 is between fog density in gram per meter cube versus visibility in kilometer. Fog density in gram per meter cube versus visibility in kilometer. We see it decreases approximately like this curve. Figure shows that variation of extent of fog in terms of density. However, it is to be remembered here that we are concerned with the radiation fog. We are concerned with radiation fog, for which fog density approaches nearly 1 gram per meter cube. But our UK non-tropical zone, Gibbons pointed out that fog occurs typically of the order of 1 to 2% of the time over a period of 1 year. The density of this type of fog is 0.02 gram per meter cube, for which the visibility is 300 meter at and is termed as moderate fog. Comparison the size of suspended water droplets. Suspended water droplets, that means fog, and wavelength in millimeter waveband. Comparing, that means if we compare the size of the suspended water droplets, that means fog, and the wavelength of millimeter waveband, the Rayleigh approximation may be adopted. Rayleigh approximation may be adopted, defining the refractivity model. Using the Rayleigh absorption approximation. Rayleigh absorption approximation 1D Hurst in 1957. The formula for refractivity is given by capital N equal to capital M bracket 3 upon 2 small m w bracket closed bracket epsilon minus 1 bracket closed upon epsilon plus 2 bracket closed ppm. Now here small mw specific weight of water 1, you already know. Capital M is defined as in equation 1. We already see here in equation 1. Capital M is nothing but mass density. What is M? Fog density. And is the complex permittivity. According to Liebe et al., we define the power loss of the radio. Here epsilon is here. This is typing mistake. Epsilon is permittivity. What is epsilon? Epsilon is the complex permittivity of the medium. That means, according to Liebe et al., we define the power loss of the radio wave while propagating through the fog. What is the power loss of the radio wave if radio waves were propagating through the fog? Alpha equal to 0.182 Fn double dash function of small f dB per kilometer, that is decibel per kilometer, where n double dash f is complex refractivity. This is complex refractivity. An attempt has been made to describe the fog attenuation at 30 and 94 GHz, considering temperatures as the parameters ranging from 284 K to 30 K. This is a pictorial present in figure 3. It is clear that within the set temperature range, figure 3. This is the figure 3. Figure 3, fog density versus attenuation curve. Fog density on the x-axis and attenuation on the y-axis. For 94 GHz frequency at different temperatures, and for 30 GHz at different temperatures, and temperature ranging from 303 to 284.7, 303.7 K to 284.7 K. It is clear that within the said temperature range, the 30 GHz attenuation never exceeds 0.35 dB per kilometer. Here we see that this is below 0.5, approximately here. So this is 0.35, less than 0.35 dB per kilometer for 30 GHz. But for 94 GHz, for same range of temperatures, fog density is 0.5 gram per meter cube, its values ranging from 2.1029 to 1.6283 dB per kilometer. Here you can easily see that it ranges from here 1.5 to between 2.2, 2.1. Okay. For the sake of clarity, it is also observed that 0.5 gram per meter cube, and for temperature 24.7 K, the 94 gigahertz attenuation is more or less 7 times larger than 30 gigahertz. Okay, this ratio becomes very much prominent to our study because we are concerned with the radiation fog whose density mostly approaches towards 0.3 to 0.7 gram per meter. This is the aim of this paper. So especially to emphasize this result, you only just consider the concepts about the general approach. What is the graph and how it is varied for different frequencies and different temperatures. It doesn't matter that the data is remembered by you or not. If you remember it, it is well. If you are not able to remember, it doesn't matter. But this graph will be explained. Okay. So in the case of advection fog, its density is less, nearly equal to 0.2 gram per meter cube, and hence this attenuation ratio is not that much prominent to be noticed in microwave propagation. To exemplify the dependence of temperature on fog, attenuation at 30 and 94 gigahertz, figure 4 has been presented keeping fog density equals to 0.5 gram per meter cube. If we taking fog density constant, in that case temperature versus attenuation for 30 gigahertz and 94 gigahertz, it is shown in the curve. Okay, so up to this we understand about that how fog attenuation at different frequencies. Here we are seeing that frequency is increasing, the effect of attenuation is increasing. At lower frequency attenuation is low, and at higher frequency attenuation is much better or much high to be considered. Next topic, estimation of rain. Estimation of rain, number 4. We already consider the third point. Here in this paper the points are not properly shown, so avoid them. We are just going to understand about the estimation of rain is not for our concern. We just consider the rain attenuation that is useful for us. Okay, how the rain attenuation is affected the microwave propagation. Okay, the rain, this is again rain estimation, not rain attenuation at frequencies about 10 gigahertz. Electromagnetic radiation starts interacting with the neutral atmosphere and with various meteorological parameters. If frequency is greater than 10 gigahertz, then electromagnetic wave interaction from neutral atmosphere and with other various meteorological parameters, in particular with the precipitation, moreover, water droplets present in the radio path acts as an imperfect conductor. The water droplets which are present in the atmosphere acts like an imperfect conductor. Hence, millimeter waves after interfacing with them cause a displacement current which is directly proportional to the frequency of the wave. Therefore, attenuation due to the presence of water droplet in the propagation path varies as the wave frequency. However, rain attenuation and scattering by rain primarily depends on the shape. It depends upon the shape of the water droplets and size of the water droplets and complex dielectric constants of the drops, and on the wavelength and polarization of the incident electromagnetic wave. So, point to be considered here, or you must emphasize this para: rain attenuation and scattering by rain primarily depends upon the first shape, second size, third complex dielectric constant of the drop, and fourth wavelength, and fifth polarization of the electromagnetic of the incident electromagnetic wave. For spherical droplets, the theory of absorption and scattering formulated by Method, and afterwards non-spherical droplets formulated by Oguchi and Hosoya. In fact, rain attenuation is characterized by non-uniformity of the rainfall intensity, raindrop number density, raindrop temperature, addition to its intrinsic variability in time and space. The most commonly used raindrop sizes were given by Laws and Parsons, Marshall and Paymer, Zos et al. For practical applications, however, the relation between the rain rate and specific attenuation, specific attenuation for a number of raindrop size distribution is approximated to simple power law in the form of alpha equal to A r raised to B. Alpha equal to A r raised to B dB per kilometer. However, to deduce the rain attenuation statistics from the rain rate data as first step, equation 4 has been used. Assuming Laws and Parsons distribution of raindrop hardens estimated theoretically the value of A and B. Theoretical values of A and B are also calculated, which the value parameters for 10, 12, 18 different frequency range were obtained for interpolation. These are the different frequencies for which these sizes are. The parameters A and B are calculated. Frequency from 11 to 100 and vertical polarization A and vertical polarization B. These are the constants which are calculated by the interpolation technique. Okay. Now the rain attenuation have been calculated for different rain rates considering Laws and Parsons drop size distribution as shown in figure 9. Figure 9 shows the rain attenuation assuming Laws and Parsons distribution. Rain rate in millimeter per hour and attenuation in dB per kilometer. Rain rate in mm per hour and attenuation in dB per kilometer. If frequency is increasing, then attenuation is increasing. Okay, according to the formula, alpha equal to A raised to B dB per kilometer, and it is given in the curve. From this curve, it was noticed that all curves increases linearly irrespective of frequencies. but the radiometric measurement shows that rain attenuation curves become saturated after a certain rate. Radiometric measurements, that means experimentally if it is observed, then these gives the data that after certain rain rate it becomes saturated. This was also observed that as we move toward the higher frequency, the saturation evolves at a lesser rain rate. To clarify the situation, we have initially started measuring rain attenuation by multi-channel microwave radiometer installed at Brazil. So this formula again we consider. This is also useful your M.SC. Rain attenuations have been measured from the brightness temperature available from the multi-channel zenith looking micro radiometer. The rain attenuation were calculated by using the relation A dB equal to 10 log 10 2m minus tau c upon 2m minus tau b. What is Tm? Mean atmospheric temperature. What is Tc? Cosmic background noise temperature. What is Tb? Brightness temperature. Okay. For tropical locations in Kolkata, Brazil, the values is given here. Okay. These are the data showing here. Figure 10 shows the cumulative distribution of measured rain rate in year. Some year it is shown monthly variation of rain rate time exceedance versus time exceeded. This is not necessary for you, you just see for your. So the rain rate attenuation exceeds also show the breakpoints for some frequencies around the water vapor. In figure 11 you can see about how monthly variation attenuation depends upon the frequency. These graphs are also showing here. So you just see here how the variation in attenuation of rain due to frequency and in different months, that means according to season. Okay, so this is the main points I described that are necessary for you for your M.SC, and also you can understand about the research papers. So this is a very good paper for atmospheric effect on the propagation of microwaves, and the points I described is described fully, and these are the results which are necessary for your M.SC topic also. So read it carefully and try to understand. Escape the many things about the data. Don't worry about the remembering the data, because in the PG classes only the graphical approach, how it is increases, how it is decreases, what is the shape of the curve, data is not more important. These are the predicted data, and some theoretical and experimental data are given here, but formula are important. So the formula and the different attenuation factors, water vapor, fog and rate attenuation, you should clarify and explain in your answer. Okay, thanks to all of you.